Hello everyone, and welcome back to another lecture video for Math 110 Introduction to Number Theory. And what we're going to talk about in this video are primes and unique factorizations. So recall that last time what we talked about was divisibility of integers, division in the division algorithm, and common divisors and greatest common divisors. So what we're going to talk about in this video are factorizations of integers, prime numbers, which if numbers are molecules, then prime numbers are the atoms, and the uniqueness of factorizations into products of prime powers. For example, 75 being the product of 3 and 5 squared. So this is the payoff of all the hard work over the last two lectures. Let's start with the definition of a factorization. So a factorization of an integer is a representation of that integer as a product of one or more numbers called the factors. So for example, all of these are factorizations of the number 300. So 300 is 2 times 6 times 25. It's also 10 times 10 times 3. It's also 2 squared times 3 times 5 squared. Or simply 300 by itself, the sort of trivial factorization. Given that there are all these factorizations, it seems plausible that unique factorizations shouldn't happen at all. But what we'll see in this video is so long as we put the factorization into a specific form, there's only one way that can happen. So one thing to observe is that each factor of a factorization of a number is a divisor of that number. So for example, let's say that we write a number as a product of three numbers, a, b, and c. Then because we can parenthesize it so that the first two numbers are multiplied by the third, then using the definition of divisibility, this shows that c is a divisor of n. Of all the integers, there are three that are special. The first special integer is 0, and it has the property that for every integer n divides 0. So I suggest that you prove as an exercise that if you're given an m that's an integer, and you know that for every integer n divides m, then you can conclude that m equals 0. And this is the sense in which that this property characterizes 0. Two other special integers are 1 and minus 1. And they have the property that for every integer n, minus 1 divides n, and 1 divides n. And again, this property characterizes 1 and minus 1. So as an exercise, suppose m is an integer, and for all integers n, m divides n, then you can conclude that m must have been minus 1 or 1. So these special integers give sort of uninteresting factorizations that we have to take into account. So for example, 22 could be written as minus 1 times 2 times 11 times minus 1 times 1 times 1. But surely we didn't need to have all of these units in there. Also, 0 has a lot of additional factorizations because we can have any number of zeros in the sequence, and we can also multiply by other numbers. And since any number times 0 is 0, that does not change which number we get. So when we are going to do factorizations, one thing is we'll only factorize non-zero numbers to deal with this problem. And also, we'll combine all the units to the front with just a plus or minus, and that's how we'll solve that problem. Before we talk more about factorizations, there are three concepts that we should discuss that happen to coincide, and they are unfactorizable numbers, indivisible numbers, and prime numbers. So I'm putting unfactorizable and indivisible in quotes because these are words that I made up for this lecture, and because they all coincide, usually we only use the word prime number to encompass all three concepts. So first, unfactorizable numbers. We define an integer n to be unfactorizable if there are two properties that hold. 1, it's not a unit, and 2, if whenever you're given two integers a and b with the property that n equals a times b, so we factorized n, then the conclusion is that a or b must have been a unit. So unfactorizable, in short, means that there are no non-trivial factorizations, where trivial corresponds to whether factors are units. The next concept is indivisible numbers. And these are numbers that, in short, are numbers that have no non-trivial divisors in the same sense of non-trivial for the previous concept. So the definition of an indivisible number is an integer n that is not a unit with the property that whenever you have an integer a that divides it, then either that integer was a unit or it's the number itself. So this is probably the definition you've heard of for a prime before. The only divisors are 1 or the number itself. And we have the plus or minus here because we're considering the integers, which just adds that little complexity of negation. The third concept, and you may not have seen this as a definition for a prime number before, but it does end up being what modern mathematics uses as the definition, is that an integer n is prime if it's not a unit, and whenever you have two integers with the property that n divides the product, then n has to divide one of the two numbers in that product. So using the Hasse diagram to illustrate this, so this is saying that if we have a times b, which of course has both a and b as factors, and if we know that n is a factor of ab, then we can conclude one of two things. Either this line exists or that line exists in the Hasse diagram, which I've written more linearly like so. And I also think about primes as being sort of particle-like. And that's in the sense that if we think of numbers as being these sorts of clouds of numberness, so if this is the cloud for A and this is the cloud for B, and we've multiplied them together, then divisibility is the property of a number cloud lying inside another number cloud. And if we have a number dividing a product, that means that it lies inside sort of the union of this region. And primality is the property that if it lies in the union, then it had to lie completely in one side. So either in this one or that one. So they're sort of like points, I like to think. Now that we've introduced these three concepts for a natural number, what we're going to do is show that they are indeed equivalent. And the first step on this project is this lemma, which is that for a non-unit integer, unfactorizability of it is equivalent to indivisibility of it. And this is essentially true by definition, but just to make everything match up and show that cross the T's, dot the I's, we're going to show that it is indeed true. So the proof is structured in the forward direction and the backward direction for the equivalence. And let's start with the forward direction. So we're supposing n is an unfactorizable integer, and we want to show that n is indivisible. So indivisibility is that whenever a is an integer such that a divides n, then the conclusion would be that a is a unit or a is plus or minus n. Okay, so given that a divides n, by definition there's some k such that n equals ak. By unfactorizability of n though, because this is a factorization of n, what we can conclude is that either a or k is a unit. So case splitting with this or, what we do is we look at case 1, which is a is plus or minus 1, or case 2, which is k is plus or minus 1. For case 1, this is exactly the left side of the goal. So that is done. And case 2, which is when k is a unit, then what we can calculate is that n is plus or minus a by plugging in k, and then by multiplying by both sides by minus 1 and if necessary, then a is plus or minus n. And that is exactly the second case. So that case is done. And so we've proved the forward direction. Now for the backward direction. Let's suppose that n is indivisible. And what we want to show is that n is unfactorizable. Okay. So definition of unfactorizability is assuming we have a and b integers that factorize n, then either a is a unit or b is a unit. That's what we want to show. But because we have this assumed factorization, then we know that a divides n and b divides n. And by indivisibility, since a divides n, we know that a is a unit, or a is plus or minus 1, and similarly, b is a unit, or b is plus or minus n. So, because we have these two ors being anded together, we can rearrange things logically and see that this implies that there are three different cases. A is plus or minus 1, b is plus or minus 1, or both a and b are plus or minus n. So if a is plus or minus 1, that's great, because that is the first thing that would suffice in this OR. And in the second case, when b is a unit, then that is the second case that we would want to prove. So for the third case, when both a and b are not units, when they're plus or minus n, then since we assume that n is not a unit, we know that the absolute value of n is not 1. And so, using the factorization, we have n is equal to a times b, and then the absolute value of a times b is the absolute value of n squared, which is strictly larger than n. And that's a contradiction. So that completes these three cases, which completes the backward direction, which completes the proof. And so indeed, unfactorizability is equivalent to indivisibility. The next step on this project to show equivalence of the three concepts is that indivisibility is equivalent to primality. So again, let's say that n is an integer and n is a unit. Then there's a forward direction and a backward direction. And the forward direction is commonly known as Euclid's lemma, because a version of it appeared way back in Euclid's original geometry textbook thousands of years ago. So let's suppose that n is indivisible, and we want to show that n is prime. So to show n is prime, we use the definition, and we suppose that we're given two integers such that n divides their product. And we want to show that n divides a or n divides b. Logically speaking, when you have an OR, it's equivalent to saying if the first case is not true, then the second case must be true. So we will rewrite this as if n does not divide a, then n divides b. And using this, we will then change we will assume that n does not divide a, and it suffices to show that n divides b. So our assumption so far is that n is an indivisible number, a and b are integers such that n divides ab, and n does not divide a. So our claim, because the goal is to somehow use Bezout's identity, is that the GCD of n and a is 1. And this is not something that we have proved yet, so we'll hide it in this proof. So by definition of GCD, we know that the GCD of n and a divides n. So by indivisibility of n, we can conclude that the GCD must be plus or minus 1, or the GCD must be plus or minus n. So let's case split on this OR, and there are two cases then. Case 1, that the GCD is plus or minus 1, and case 2, that the GCD is plus or minus n. So since GCD is non-negative, we know that the GCD isn't minus 1, and instead it's 1, and that's exactly what we wanted to show for this claim. Case 2, that the GCD of the two numbers is plus or minus n, then well, since by definition of GCD, the GCD of n and a divides a, then because we know that this GCD is plus or minus n by this assumption for this case, then in fact n divides a. But our assumption was that n does not divide a, and so that's a contradiction. So this case cannot happen. So we've handled all the cases, so the claim is indeed true, that the GCD is 1. Okay, so now by Béziers identity, there are integers x and y such that xn plus ya is equal to the GCD, which is 1. And this is a very useful equation right here. Because one thing is, we know that n divides n times b, because we're just scaling n. And we also know that n divides a times b by assumption. And so by that linearity property of divisibility that we saw in the previous lecture, we know that n divides xnb plus yab by multiplying each of these two right-hand sides by x and y and adding it together. But this thing that we just showed that it divides, we can factor a b out, and one of the factors is 1, so it's actually saying that n divides b, which is exactly what we wanted to show. So that's the forward direction. The backward direction I'm going to leave as an exercise because it's fairly straightforward, but I'll leave a sketch and I'll explain a little bit about it. So remember, for the backward direction, we're assuming that n is prime and we want to show it's indivisible. So we assume that we have some integer a that divides n, and we want to show that that integer was either a unit or plus or minus n. So if we do have that a divides n, then by the definition of divisibility, there's some b such that n equals ab. And when you have an equality, we can also less strongly have it that it's a divisibility, because we can just use 1 in the definition. So n divides ab. But because n is prime, n has to divide a or b. And so, for example, if n divides a, so this would be one of the cases, then we can use the definition of divisibility to say there's a k such that a equals kn. And so by substituting, we have that n equals knb, and because n shows up on both the left and the right, we can cancel it because n is not 0, and because it's prime. And then we can conclude that b must be plus or minus 1. So anyway, and then you continue in this sort of way for the other case. Okay, so with those two lemmas, we've now actually shown that the three concepts are equivalent. So I'll summarize them in this theorem. So if we have an integer that's not a unit, then n is prime if any of the following equivalent statements hold, which means that we can take 1, 2, or 3 as the definition, but it's worth always remembering all three properties. So the first property is whenever you have a and b being integers that factorize the number, then it had to have been a trivial factorization. 2, whenever you have a divisor of the number, then it had to have been a trivial divisor, namely either a unit or the number itself, or negative the number. And then 3, the primality property, which is that whenever we have two numbers whose product our number divides, then the number had to have divided one of the two factors. Okay, so that is what primality is. So as some very simple examples, we know that 2 is prime, and that's because its only divisors are plus or minus 1 and plus or minus 2. And another example is minus 2. And that's because, well, whenever we have a prime, we can multiply by minus 1 to get another one. It should be noted that sometimes only positive numbers are considered to be prime, but we're just using these properties to define them in this lecture. Now that we know what primes are, on our way to understanding factorizations, a useful concept is composite numbers. And composite numbers are all the remaining numbers that we have not discussed so far. So if it's a number, n is composite if it's not 0 or a unit, so if it's not one of the three special numbers, and if it's not prime. And to explain this terminology of composite, because this definition does not make it clear, is the following lemma, which restates this in a different form. So an integer is composite if there exists integers a and b which factorize it such that the numbers are not units. So a number is composite if there's a non-trivial factorization. So here's the quick proof. So let's suppose that we have a composite number on hand, and by contradiction, let's assume the opposite of the conclusion, which is that for all a and b, if n equals ab, then a is a unit or b is a unit. But since composite implies n is not 0 because it's part of the definition, then n is prime by the definition of prime. But that's contradicting n being composite because n is not prime. So that's that. Okay, so just summarizing again, composites are the non-zero integers with non-trivial factorizations. They're compositions of some kind. An important ingredient to unique factorizations is that factorizations exist at all. And that is what this lemma shows. So a prime factorization is defined to be a factorization where every factor is a prime number. And so suppose that we have a natural number, and we'll deal with just natural numbers to avoid all the plus and minus business. And let's say that's neither 0 nor a unit. Then the conclusion is that it has a prime factorization. And the way this works is actually very algorithmic, which we'll see in the next slides. But the way that the algorithm is encoded is using well ordering. So to apply well ordering, let's let S be the set of all natural numbers with the property that they're neither 0 nor 1, and also that the number doesn't have a prime factorization. What we want to do is show that S is actually the empty set, and if it's the empty set, then that means everything has a prime factorization with these hypotheses. So for contradiction, let's suppose instead that it's actually not the empty set. So by well ordering, there is some number inside of S that is least. And so it's some number that's neither 0 nor 1 and which doesn't have a prime factorization. So one thing that we know is that n is not a prime number, because if it were a prime number, then n equals n is a factorization with prime factors, just a one-factor factorization. Then by the definition of composite, since we assume that n is neither 0 nor 1, and also that it's not prime, it's composite. So by that previous lemma, since it's composite, there are some natural numbers a and b such that n is the product of a and b, and neither of a or b is 1. So in other words, there is a non-trivial factorization into two natural numbers. And what we can see is that since neither of them is 1, that it must be the case that a is less than n and b is less than n. Because if either were n, then the other number would be 1. And since n is least, that implies that a and b are not elements of S, and so they have prime factorizations. So then the idea is you take the prime factorizations that exist for both a and b and just juxtapose them together. You take the product of the prime factorizations for both a and b, and that is a factorization for n. And it's a prime factorization because it's giving it in terms of prime factors. So that's that. The proof of that lemma gives a sort of algorithm for finding prime factorizations. Not necessarily a very good one, but it's an algorithm nonetheless. The way this works is, suppose we're given a natural number that's greater than 1. Then what we do is we try dividing it by 2, 3, 4, and so on, all the way up through n minus 1. And if there are no divisors, after checking all this, then n is prime, and so n equals n is the prime factorization. And otherwise, let's let a be the divisor, and let b be the division of n by a. And so we get these two natural numbers, a and b. And we note that a is strictly less than n, and also because a is not 1, b is strictly less than n. And so we can recursively apply this algorithm for a and b to get two prime factorizations of a and b. And then we juxtapose them. We just put them all on a line, product together. That's the prime factorization. One interesting fact about this is that actually, if we take a to be the first divisor from this list, then it's prime. So we only have to prime factorize b. Not that that really makes this algorithm that much more efficient, if at all. For sake of illustration, here's an implementation of this algorithm in Python. And the way this works is, given an integer n, then we maintain a list of all the factors we know so far. And okay, so there's this loop, which is so long as n is still greater than 1, then we consider all numbers in the range from 2 through n minus 1. That's what range means in Python. And we check to see if the remainder after division by that is 0. And since we're doing it in order, if it is 0, that means that p is prime, and also it's a factor of the number, so we add it to the list of factors so far. And then we replace n with n after dividing by p. Then what break does is it comes back and begins this loop anew, using this new n. And it keeps updating this factors array. If there were no factors that we found in this loop, then what happens is that we know that there are no non-trivial divisors, so instead n is prime. So then instead we add n itself to the factors list, and then leave this loop, and then return factors as the list of factors. So for example, if we factorize 480, then this algorithm ends up creating a list of 2, 2, 2, 2, 2, 3, 5, and these are the factors, and it gives a factorization, or which we can write as a prime power factorization. This is not a very efficient algorithm, and we can improve it considerably, but at least this shows that it's something that even a computer can do. It does not take any creativity, just perseverance. Before we get into factorizations proper, let's take a diversion into the infinitude of primes, which is a proof again by Euclid. And the claim is that the set of all prime numbers is infinite. So there is not a finite list of all the prime numbers out of which all other numbers are products. And the proof is elegant and very short, given everything that we've developed. So for sake of contradiction, let's suppose instead that there is a finite list of primes. And let's let p1 through pk be all the prime numbers that we know. So let's let m be the product of all the primes plus 1. So this number, it might not be prime itself or anything like that, but it is a very interesting number because what we'll show is that it has a factor that is not in the list of prime numbers so far. Okay, so since m is some number and we've shown that every number has a prime factorization, then there is some prime that divides it. So let q be such a prime that does divide it. And since we assume that this is the list of all the prime numbers, then there's some I for which q equals pi. And a consequence to this is that we know that q divides the product of all the primes that we know. Okay, so since 1 is equal to m minus the product of all the primes, then by the linearity property of divisibility, the conclusion is that, well, since q divides m and q divides this product, q must divide 1. But if q divides 1, that means that q has to be plus or minus 1. But plus or minus 1 is not a prime. And so therefore, we've reached a contradiction. And so therefore, there must have actually been infinitely many primes. One more thing before getting into prime factorizations and their uniqueness is the problem of how do we enumerate all the primes? how do we make a list of all the primes out to any size? And one not so good algorithm, but does work, is we consider every number one at a time and then go through and try to see if it has any divisors other than one in itself. And that does work, but that's quite a lot of addition. So Eratosthenes came up with another approach, and this is known as a sieve. And the way that this works is that we use the primes that we've seen so far to just quickly remove all the possibilities for other numbers that are that have it as a divisor. So I'll show you by way of example. So by definition, neither 0 nor 1 is a prime. And now 2 is a number that has not been is the first number that has not been crossed off. So we say that that is a prime. And then what we do is we cross off every other number. Every other because we're crossing off all the multiples of 2. So almost done. Okay, all the multiples of 2 have been crossed off. Now what we do is we look for the first number that is not crossed off, and that would be 3. And then we cross off every multiple of 3. So 1, 2, 3, double cross off. Okay, now 5 is the first number that has not been crossed off so far. Okay, so we cross off 10 is already crossed off, then 15, 20, 25, 30, 35. Then 7 is the first not crossed off. So we have 7, 14, 21, 28, 35. Then we have 11, the first number not crossed off. And then we cross off 22 and 33. Then there's 13. And then we cross off 26, which is the first multiple. And then there are no more multiples. Then we then we get 17. And so the next would be 34. And then we get 19, which we cross off 36, and then 23. And actually, all the remaining numbers here are prime, because all the multiples would be off the end of the list. So we have exhaustively enumerated all the prime numbers less than or equal to 39. So with a large enough table and enough patience, you can enumerate the prime numbers in any range. Okay, now that we know about primes and we know about existence of prime factorizations, the big question is whether we have uniqueness of factorizations, because that's always how it is in math, existence and uniqueness. So for the uniqueness question, though, there are a couple of issues to get around. And that is that on the face of it, factorizations are not unique. For example, 15 is both 3 times 5 and 5 times 3. And 27 is both 3 times 3 times 3, or minus 3 times minus 3 times 3. So a solution to this issue, it's a straightforward solution, and that is to choose some sort of normal form. So the normal form that we choose here is we make sure that all the primes that we consider are positive, so no negative primes, and then we have a plus or minus out front, which is a plus or minus 1 times the rest. And then also, to avoid this reordering problem, we say that our normal form has it where each of the primes that appear are in ascending order, or more specifically, non-decreasing order. So what we'll do is show that this normal form for prime factorizations of a number that's not 0 is in fact unique. Just to show you the normal form for these, so this would be 3 times 5, and then this one would be minus 3 times 3 times 3. And for convenience sake, it's not so nice having multiple copies of the same prime appear. We want to coalesce them all into exponents. So instead what we'll consider is the normal form of prime power factorizations. So each of the primes that appear is strictly larger than the previous one, and they all have exponents, possibly 0, possibly 1, that they are raised to when we multiply it together. So for example, 24 is 2 cubed times 3. That is the normal form for it according to the prime power factorization. The reason for considering prime power factorizations is that the way we're going to prove unique factorization is using a more modern approach than the one that appears in the textbook. And that is considering the multiplicity of a prime in a number, which is also known as the order of a prime in a number. So here's the definition of this more formally. Let's let p be a prime and n a non-zero integer. The order of p and n is the maximal natural number k such that p to the k divides n, and so maximal means that p to the k plus 1 does not divide n. And we write ord sub p of n for k, this maximal power of p that appears in the number. So using the example of 24, the ord sub 2 of 24, so the multiplicity of 2 in the factorization of 24, is 3. And I sort of slipped when I just said that, because what I actually mean is that 2 to the 3 divides 24, but 2 to the 4 does not. And the whole point is that ord is going to be what lets us calculate the prime factorization in a way. So for another example is ord sub 3 of 24 is 1, because the exponent of 3 is implicitly 1 here. Or another, ord sub 5 of 24 is 0. So these ord functions for varying primes are measuring the amount of a particular prime that appears. So again, using the chemical analogy, if numbers are molecules, then this is saying how many of a particular atom appear. So to show prime factorization, all we need to do is show that ord sub pi of n is equal to mi, because that if we had any other factorization, then we can apply ord to both sides and see that the exponents are all the same. So that is what we will do. And to do that, we'll show a few properties about ord that will make this all very easy. The first property is that ord of a product, assuming that both of the numbers are non-zero, is the sum of the ords. So if you've taken algebra, this is saying that ord is some sort of homomorphism. But we don't need that terminology here. So here's the proof. Okay, so we've got a and b integers and p a prime. And because, and by definition of ord, there are some integers c and d such that a equals c times p to the ord p of a, that's sort of a mouthful, and b equals d times p to the ord p of pb, with the properties that p does not divide c and p does not divide d. The reason that this is what ord means is because if p, well, first of all, p to the ord is supposed to divide the number a. And second of all, if p did divide this number c that comes from the definition of divisibility, then we could have divided c out, or divided c by p to make c smaller, and instead put that p factor into this power and make ord 1 bigger. So anyway, that means that p does not divide c. And similar, p does not divide d. Okay, now that we've written a and b in these forms, then we have that a times b is c times d times p to the sum of the powers. And hence, by definition of divisibility, p to the sum of these ords divides A times B, where C times D is the constant appearing in the definition of divisibility. So the claim is that if we add 1 to this exponent, it does not divide AB, because if this is true, then by definition of ORD, this number here, the sum of these ORDs, is the ORD of AB. Okay, so let's prove the claim. And we'll do it by contradiction. So we assume that it did divide. And if it did divide, then there'd be some k in the integers such that A times B equals k times p to the sum of ORDs plus 1. But on the other hand, AB from before is C times D times p to the sum of ORDs. And from this, by factoring out ORD p to the sum of the ORDs, then what we have is that k times p is C times D. So that I'm using the cancellation law. And by definition of divisibility, p divides C times D. And because p is prime, p divides C or p divides D. But that's a contradiction because of our assumption there. And so therefore, the sum of the ORDs is indeed the ORD of the product. Now that we've proved that mean lemma, there are 3 more lemmas that we need to make the proof of the unique factorization very straightforward. The first one is that whenever we have a prime, then ORD P of a unit is 0. So 1 just does not contain any primes inside of it. And so just using the definition of ORD, we can show that P to the 0 divides plus or minus 1. So 0 is a possible value for ORD. And that is because p to the 0 is 1, and 1 certainly divides plus and minus 1. And also, p does not divide plus or minus 1. And we saw that in an earlier proof, but another reason for this is that that p is greater than 1. So there's no way that p could divide plus or minus 1. The next lemma that we need is that if p and q are primes, then ORD P of Q is 1 or 0 depending on whether or not P equals Q. So you can tell how much of a particular prime is contained in another prime, and that is 1, but only if they're the same. So the proof depends on this claim, that if P divides Q, then P equals Q, assuming our assumption, which is that P and Q are primes. So here's the proof of this claim. Since Q is prime, then the fact that P divides Q using the indivisibility property, then P equals 1 or P equals Q. And since P is a prime, we know that P can't be 1, and so the conclusion holds, which is P equals Q. Now we consider this by 2 cases. Case 1 is that P equals Q, and case 2 is that P is not Q. So if P equals Q, then we can see that P divides P, of course, and also P squared does not divide P. And we can consider this by magnitudes, that P squared's absolute value is greater than the absolute value of P. And by definition of ORD, ORD sub P of P is 1. So we have shown that this value of 1 does happen when P equals Q. For the other case, when P is not Q, then by the claim, applying the contrapositive of it, which is if P is not Q, then P does not divide Q, we have P does not divide Q. And so, since P to the 0 divides Q, ORD can possibly be 0, but also P does not divide Q, so P to the 1 does not divide Q, so ORD is exactly 0. So that completes that lemma. And then finally, I won't prove this completely, but I will give you a sketch, and I invite you to do as an exercise. And that is that if we have an integer a, where a is not 0, and we have integers n and p, where p is prime, then ORD p of a power of a is a scale multiple of ORD p of a. So just like before, products turn into additions, and exponentiations now turn into multiplications. So ORD should really be thought of as some sort of logarithm. So the proof of this, the sketch, is that ORD sub p of a to the n is ORD sub p of the product of n copies of a. And so repeatedly applying the addition rule that we came up with, we have that this is the sum of n copies of ORD p of a, and so we can combine it all into just n times ORD p of a. But to make this proof completely formal, it really ought to be done using induction. So that's why this is an exercise. Now we are ready for unique factorization, and this is everything we've been working towards. So the theorem. Suppose we have a prime power factorization in normal form. So each of these primes are, well, each of these PRs are prime, and each is strictly less than the next. And then what we can do is for each I calculate that mi is ORD pi of n. So what this means is if somebody gives you a prime power factorization, then you can, of a number, you can tell them what each of the exponents are by just seeing how many times with multiplicity does a particular prime divide the number, and then you can write it down. And so that's why it's unique, because any two such prime power factorizations must indeed be equal. So here's the proof, also done a little bit sketchy because there is an induction step in here that ought to be made completely explicit, or at least proved as a lemma. So we calculate that ORD sub pi of n is by substituting in our prime power factorization, ORD sub pi of plus or minus 1 times p1 to the m1 times p2 to the m2, and so on up to pk to the mk. And then repeatedly using the multiplication to addition lemma, and this is where the induction step should happen, we have that this is the sum of ORD sub pi of plus or minus 1 plus ORD sub pi of p1 to the m1 plus and so on, all the way up to ORD sub pi of pk to the mk. So one of our lemmas was that ORD of plus or minus 1, no matter the prime is 0. And then inside of here, since all of the primes are distinct from each other, exactly one of them will be pi. And for that one, by the other lemmas, we see that it is mi. So in particular, what I am using is that ORD sub pi of pj to the mj is equal to m sub j ORD pi of pj, which is equal to mj if I equals j, and 0 otherwise. Okay, and so we see that ORD sub pi of n is mi. And that is unique factorization. Now let's look at a bit of an application of that, and that is to explain divisibility. Because remember last time we were looking at Hasse diagrams, and one of them was the Hasse diagram for the divisibility of natural numbers. So what this theorem does is says that if you have two natural numbers m and n, then m divides n if and only if for every prime the amount of p in m is less than or equal to the amount of p in n. So for example, 2 to the third times 5 times 13 divides 2 to the third times 5 squared times 7 to the fourth times 13, because 3 is less than or equal to 3, 1 is less than or equal to 2, 0 for 7 is less than or equal to 4, and 1 is less than or equal to 13, and 13 is less than or equal, and 1 is less than or equal to 1. Or another example, we can say that 2 times 3 does not divide 2 squared, because while 1 is less than or equal to 2, 3 is not less than or equal to, and 1 is not less than or equal to 0. So that's what this theorem will allow us. Okay, so let's prove it. So let's say that we have a list of all the primes that appear in both m and n. Or not both, but I mean among m and n. So so we can write m and n as these prime power factorizations using these prime numbers, where we have these powers a1 through ak and b1 through bk that appear as these ords. Okay, so let's run through. We will prove this not by going forwards and backwards, but instead by having a sequence of equivalences. Okay, so m divides n is by definition that there exists some integer d such that d times d times m is n, and which I substitute our factorizations into. And so this is equivalent to by using the fact that every prime that divides d must also divide n, and by the primality property that means it must divide one of the primes in this list. Then that means that it has a prime factorization using all the primes that we have in our list. So there are these natural numbers that we can use to factorize d. Okay, so because this is a product, we can then add up all the exponents just as an algebraic manipulation. And then what we can see is that by calculating ords on both sides, that ord, for example, ord pi of ci plus ai is equal to, and by calculating ords, for example, if we calculate ord pi of both sides, we get ci plus ai is equal to bi. And then by definition of less than or equal to, we have for all I, ai is less than or equal to bi. Which, just rewritten in terms of ords, is this is the conclusion that we wanted. Okay, so to check divisibility, if you have prime factorizations on hand, all you have to do is compare all the exponents for less than or equal to. With this theorem in hand, what we can now do is fully understand the Hasse diagram for the natural numbers with division, or with divisibility. And so the key is that, one, we can prime factorize all of the numbers into prime power factorizations, and two, to check whether one number is lower than the other number in the Hasse diagram with a line, then we have to merely check the powers for each prime and that they're less than or equal to. So down at the bottom we have our unit 1, and up at the top we have 0, and the first layer are all the primes, the ones where they are the only number that appears in this prime power decomposition. And then for the composites, those are everything that is remaining. And specifically, a line exists if the difference between two prime power factorizations is just 1, in the sense that if you sum up all the exponents of one number, you get one more than the sum of the exponents of a lower number. So it's still sort of a tangled mess, but at least we know exactly how to predict what it will look like. In summary, what we saw are that primes are the multiplicative atoms of the positive natural numbers, where we're thinking of numbers as being these molecules consisting of primes as atoms all stuck together. And the way that we can measure how much of each of these primes appear in each natural number is this ord sub p function, which gives you precisely how many times a prime, what's the highest power that a prime will divide a particular number. And with this, we have the unique prime power factorization that all other factorizations after being put into normal form must be equal to. Using product notation, which is a capital pi instead of a capital sigma, we can write this as n is plus or minus the product over all positive primes, all infinitely many, of p to the power of ord sub p of n. So this is an infinite product, but the interpretation is that since ord sub p of n is going to be 0 for everything but some finite list of primes, this will be a finite product in the end. And anyway, this is just a formal way of summarizing what we saw. And using Euclid's argument, we saw that there are indeed infinitely many primes. So there's not just a single list of numbers such that every number is of the form p1 to the a1, p2 to the a2, and so on, up to pk to the ak. A given number might involve arbitrarily many primes in its prime factorization. Now, you probably have a lot of experience with prime factorizations through the years, so maybe you're not super surprised by this result. But I just want to conclude with the fact that there are number systems which fail to have unique factorization. So in that sense, unique factorization is a big deal. And also, not to mention that many theorems that we're going to see depend on unique factorization holding. So for example, there's this number system where it's numbers of the form a plus b root minus 5, where a and b are integers. So it's the subset of the complex numbers of numbers only of this form. And these sorts of number systems are what algebraic number theorists study. And the interesting thing about it is that 6 fails to have a unique factorization. On one hand, it's the product of 2 and 3, but on the other, it's the product of the conjugates of 1 plus root minus 5. And one thing you can show is that 2, 3, and the conjugates of 1 plus root minus 5 are indivisible numbers. So there are these two different factorizations of indivisibles, and also these indivisibles are not prime numbers, as this shows. Well, I hope you enjoyed seeing how every number has a prime factorization that's unique, and I'll see you next time.